Hey, this is Math 105, Section 2.6, Part A. So we're looking at the sums of functions, so how we're combining functions. First, looking at f of g, f plus g. So what we do when we say f plus g of x, that notation means we're just adding f of x plus g of x. Okay, so that's called the sum of the functions, and its value at x is just evaluate the function at f, and then evaluate at g, and then just add those two. Okay, so. The sum only makes sense if both f of x and g of x are defined, or that means if x belongs to the domain of f and also the domain of g. So x has to be able to be part of the domain of both functions. So just simply we're just adding the two functions. F plus g of x is f of x plus g of x. So let's say the domain of f is a and the domain of g is b, two different functions. Then the domain of f plus g is just the intersection of those. So that would be a and b, okay, the intersection of the two domains. Okay. We can also do the difference of two functions, so f minus g, a product, f times g, and a quotient, f over g, of the functions f and g. Okay. So just kind of looking at those, f minus g of x is f of x minus g of x. Our domain is a and b. Okay. F times g of x is going to be f of x times g of x. Our domain is a and b. Okay. And then f divided by g of x is just f of x over g of x, where the domain is x is an element of a and b such that g of x is not equal to 0. So we just can't have 0 in the denominator there. Okay. So in this case, we're just dividing the functions. Okay, so let's look at an example first. Let's say f of x is 1 over x minus 2, and g of x is square root of x. Okay, we're going to find these functions, f plus g, f minus g, f times g, and f divided by g, but let's do their domains first. So domain of f is x is not equal to 2, because we can't have 0 in our denominator. Domain of g is x is greater or equal to 0, because we have a square root there for x. Okay, so we're going to take the intersection of these two domains, and when we do that, we get x is greater than or equal to 0 and x can't be equal to 2, right? So that would be, we can start at 0, we can go up to 2, we have to skip 2, and then union, so we go past 2 to infinity. So anything positive or 0 but not 2. Okay, so those would be the intervals there. So we're taking the intersection of the domain of f and the domain of g. Okay, now let's look at f plus g of x. So that's just f of x plus g of x, which is 1 over x minus 2 plus square root of x. Okay. F minus g of x is f of x minus g of x, which is just 1 over x minus 2 minus square root of x. F times g of x, so you'll see fg next to each other, that just means f times g, which is just f of x times g of x, which is square root of x over x minus 2, so we're just multiplying the two functions. Okay. And then finally f over g of x, which is f of x divided by g of x, which is 1 over x minus 2 divided by square root of x, which is 1 over x minus 2 times square root of x in the denominator. Okay, so we have to exclude 0 in our denominator because we can't have 0 in we have to exclude 0 because g of 0 can't be 0. Okay, so this case we can say x is greater than or equal to 0 and x is not equal to 2. Okay, so let me rewrite those domains here. Okay, so for the first three, f plus g, f minus g, and f times g, domain would be x is greater or equal to 0 and x is not equal to 2, because we can't have 0 in a denominator and we have to have a positive or 0 square root. Okay, for f over g of x, we have to make one extra stipulation. X can't be 0 because that gives us a 0 in the denominator here. So our domain for the last one is x is greater than 0 and x is not equal to 2. So we don't have the equal to there. Okay, but for these three you do. Okay, now let's evaluate these four functions at 4. So f plus g of 4 is f of 4 plus g of 4, which is 1 over 4 minus 2, plus square root of 4, which is 1 half, plus 2, which is 5 halves. F minus g of 4 is f of 4 minus g of 4, which is 1 over 4 minus 2 minus square root of 4, so that's 1 half minus 2, which is minus 3 halves. F times g of 4 is f of 4 times g of 4, so that's 1 over 4 minus 2 times square root of 4, which is 1 half times 2, which is 1. And then finally, f over g of 4 is f of 4 over g of 4, which is 1 over 4 minus 2 times square root of 4 in the denominator, which is 1 over 2 times 2, which is 1/4. Okay, So if you're just evaluating a number, you can do that directly. You don't have to find f plus g of x, for example, or f minus g of x. But it can be helpful to do that because then you can evaluate it for different numbers other than than just the 4. Okay, we can graph the function f plus g by what we call graphical addition. That just means that we add the corresponding y coordinates for each point. So what we're doing is we're adding up the y values and getting our new graph. So for example, let's say this is our y equals f of x, and this is our y equals g of x. This one is a nonlinear function. This one is linear. So we add those two. We're saying y f of x plus g of x. We're going to add this y value and add this y value. So we're going to get something up here. And same with this. We're going to, like here, we would add this y value and then add this y value. So we're going to get something up here. Okay. So here's what it looks like. You see, when we add those two, we get this purple one. Now notice that we're not just shifting the red one up because we're adding a value that's increasing every time. Think of that we're taking these y values, right, and we're adding these y values, which increase. So what happens is that it takes that curve and kind of pulls it up and stretches it out a little bit. So you can see that we go from the red to the purple when we add the blue. Okay, so we're adding f of x plus g of x, which we're adding the full y value, and then it goes up to here. Okay, so that would be the graph of f plus g of x. Okay, kind of the more important topic in this section is the composition of functions. This is where we're going not adding or subtracting or multiplying or dividing functions, but we're actually going to go through each function in a row. Like we might go through f of x first, and then g of x, or we might go through g of x first and then f of x. So you think of we're going through them in series. Okay, first we go through one function, then we go through the other one. Okay, so suppose our f of x is square root of x, and our g of x is x squared plus 1. Okay, what we do is we can define a new function where we look at this thing called f of g of x. Okay, and that we say that g of x is nested in here. So basically what we're doing is we're putting x through g to get g of x, and then we're putting it through f. Okay, so we're actually going through two functions. We're going to go through g of x first, that inner function, and then we're going to take the output of that and go through f of x. Okay, so we'll call that h of x. So h of x is f of g of x, which is f of x squared plus 1, because that's what g of x is. Okay, so we're going to put x squared plus 1 into this function, f function. So it can be helpful to do this. Write your outer function with blanks. So f of blank equals square root of blank. Then when I put something different in f, like x squared plus 1, I can just put it in the blanks here. Okay, so f of x squared plus 1 is going to be the square root of x plus 1. Okay. So given number x, we first apply the function g to it, then apply f to the result. Okay, and remember we talked about functions as rules. We can say the function f is the rule, take the square root. G is the rule, square, then add 1. And then h, because we're taking the composition, is h is the rule, square, then add 1, then take the square root. Okay, so we're going to do g first and then do f with the result. Okay. So we kind of also look at this as sort of like a black box or machine. Our input is going into x first. Sorry, our x is going into g first, and then out comes x squared plus 1, because g of x is x squared plus 1. And then we take that output and put it into f. So now we're going to take the square root of x squared plus 1 to get our result. Okay. So the h machine, or the h box, is composed of the g machine first and then the f machine. Okay. And that looks like this. Again, the notation would be f of g of x. Okay. Now we also use this notation, f of g of x. Okay. Where you have that circle there. It's not a times, it's a little circle. Okay, so that this is the composition. So these mean the same thing. F of g of x with the brackets is the same of that f circle g of x. Okay. And that means we're going through the second function first. We're going to go through g first. Here we're going through g first, and then through f. Okay, so basically, we're going to start with the number x. We're talking about f of g of x. Okay. we're going to start with the number x in the domain of g. Okay, so it has to be the domain of g, and then find its image g of x, which is the output. Okay, and then if that number g of x is in the domain of f, we can then calculate the value of f of g of x. Okay, so that's how we get this new function h of x equals f of g of x. Okay, so that's called the composition or composite of f of g. Okay, so here's what our composition looks like. Composite function or composition, f circle g would be written like this. We have f circle g of x equals f of g of x. So this is just two different ways of showing the same thing. But when you see the circle, remember we're going through the second function first. We're going through that g first, and then through the f. And then on this side, we're going through the inner function, then the outer. Okay, if we talk about the domain of f of g, it's the set of all x in the domain of g, such that g of x is in the domain of f. Okay. In other words, f of g of x is defined whenever both g of x and f of g of x are defined. Okay, so we have to find x where g of x is defined and f of g of x is defined. So we have to think what outputs work to go into f. You know, what outputs of g of x will go into f. Okay, so here's our x, goes into g of x first, then that output goes into f. Okay, so that's how we get f of g of x, and that composition is the whole process there. Okay, so let's look at an example where f of x is x squared and g of x is x minus 3. Let's find f of g and g of f, okay, and their domains. Okay, so f of g of x is f of g of x. We can write with parentheses. So we're going to put g of x first. Okay, so remember g of x is x minus 3. So that's just f of x minus 3. Okay, so we're going to take f. Now this is where we want to take the outer function and write it with blanks to get a better idea of what we're doing. But f of blank equals blank squared. So whatever we put into f is going to be squared. Okay, so f of x minus 3, we're going to square x minus 3. So there we are. So the f of g of x is x minus 3 squared. Okay. Now let's do the opposite. Let's do g of f of x. That means we're going to go through f first. Okay, the inner function here. So remember, f of x is x squared. So that g of f of x is g of x squared. Okay, and then here we want to do blanks again to show what our outer function with the blanks. Remember, g of blank is blank minus 3. So we're going to take g of x squared, which is x squared minus 3. So that's g of f of x. And we're doing the f first, then the g. Okay. Now the domains of both are real, okay, because there's nothing that we can't do for x in this. You know, there's no denominator we have to worry about, and there's no square root or anything like that. So but for both of these domain of compositions, the domain is all real numbers. Okay, so let's evaluate them at different numbers. Remember, f of x is x squared and g of x is x minus 3. So f of g of 5 would be f of g of 5, so we're going to take g of 5 first. G of 5 would be 5 minus 3, which is 2. So that gives us f of 2. And now we're squaring, so f of 2 is 2 squared, which is 4. Okay. And then f of 7, we're going to take f first. So that would be g of f of 7. Okay, remember, f of 7 would be 7 squared, so that's 49. So then we take g of 49, which is 49 minus 3 is 46. Okay, so we can see that, at least, you know, from the last example, in general, f of g is not equal to g of f. That we're doing, you know, if we do one before the other, we'll get different results. Okay, so if you go through the functions in different order, you don't always get the same result. Okay, all right, we can also do more than 2 functions. We could do the composition of 3 functions, f of g of h, which means we're going to do h first, then take g of that, then take f of that. So we do function h, then function g, then function f. Okay, that would be composition of 3 functions. Okay, so let's look at f of g of h. If f of x is x over x plus 1, g of x is x to the 10th, and h of x equals x plus 3. So we're going to do h of x first. You know, we start from the last, so we do h, then g, then f. Okay, so h of x is x plus 3, so we're going to take g, f of g of x plus 3. So remember, now we'll do the little thing with blanks. So g of blank equals blank to the 10th. So we're going to take g of x, or g of x plus 3, which is x plus 3 to the 10th. Okay. And then we're going to take f of that. So that's our outer function. And we can say f of blank. Let me put that over on the side here. F of blank equals, sorry, that should be equal to, equals blank over blank plus 1, where I'm putting in blanks for x. Okay. So when we have it this way, now we're going to take f of x plus cubed to the 10th. So we have x plus cubed to the 10th here, and x plus cubed to the 10th here, because we're evaluating f at x plus 3 to the 10th. Okay. So x plus 3 to the 10th, and then x plus 3 to the 10th plus 1 in the denominator. Okay, so that would be f of g of h of x. Okay, so far we've been composing functions with using different functions, but sometimes we want to decompose. In calculus, it can be useful to decompose a complicated function into simpler ones. In other words, we're breaking it down into smaller functions. So we've built up larger functions for smaller ones. Now we're going to do the opposite. So for the larger function, we're going to use a capital letter just to show that we're going to break it down into smaller pieces. So think about this function. This capital F of x is the fourth root of x plus 9. Okay? And we want to find two functions, little f and little g, composition of the two, f of g, where we can get that bigger function. So kind of think of the steps here. Like the first step is you take x and add 9. And then the second step is you take the fourth root, right? So we can, if we're going to do f of g of x, we're going to do g first. So think of g as our first step. So g of x would say take the input and add 9. F of x says take your input and take the fourth root. So think of your second function again with blanks. Okay, so f of blank equals the fourth root of blank. Okay, and that says that this function takes the fourth root of whatever its input is. Well, its input is going to be x plus 9 because we've already done that with the g. Okay, so but we write it generally with x as our input. You know, so this function says take x as your input and take the fourth root. Okay. Well, we're not going to use x as our input. We're going to actually use x plus 9 as our input when we do this composition. So we can say, okay, we're going to take f of x plus 9, which gives us the fourth root of x plus 9. Okay. So the inner function, or the one we go through first, will be add 9 to your input. And then this just says take the fourth root of your input. Okay. So there's our composition. First we add 9, then we take the fourth root. Okay, so f of g of x is f of x plus 9. Let me write that down here. Okay. So we already did the x plus 9 with the g of x. Now we're going to let function f do its thing, which is take the fourth root. Okay, so here's f of x plus 9. And when we do that, we're just taking the fourth root of x plus 9, and that gives us our capital F function. Okay, so we can break this function down into steps. In this case, 2 steps. So what we're doing is decomposing this larger function, capital F of x, into 2 smaller functions, which kind of breaks the steps up into, smaller steps. We'll look at some more, little more complicated examples of this in class.